Hey folks, and welcome back to our next calculus lesson. We're going to continue with optimization problems, section 8.3 in your textbook, and we're actually going to extend to 3 dimensions today. So it's going to show a lot of what we've been doing in 2 dimensions, how it relates to 3 dimensions, as well as how it relates to a couple of lessons you had in geometry. We're still going to be doing the same thing of getting the equation into one variable, taking the derivative, setting the derivative equal to 0 to find the critical points, and that'll be our maximum area. Let's take a look. So here we have an example. Our aim is how do we optimize 3D shapes. And what we're going to be looking at today is an example from your textbook about how to do just that. Go ahead and read this problem out. If you want, you can either look in your textbook on this page, or you can pause and write it in. Now I've drawn a sketch of it over here. We have our parabola drawn out in black, we have the cylinder drawn out in pink, and we have a point where the cylinder touches the paraboloid in blue. Now, just like everything else, we want to make sure that we can write our equation out in terms of just one variable. So this is just going to be x, and this would be y. However, we know what y is. Y is equal to 9 minus x squared. So this is just 9 minus x squared. Nice thing is now we have the volume, which is written all in one variable, and we can just take that and rewrite it as 9 pi x squared minus pi x to the fourth. There, now our volume of the cylinder is all in one variable. Like we're going to do before, we're going to find our derivative. So that means that our derivative is going to be 18 pi x minus 4 pi x to the third. We're going to set it equal to 0 as we have done before. 18 pi x is equal to 4 pi x to the third. So do a bit of algebra and we're going to get x is equal to positive or negative square root of 4.5. Cool. Now the thing is, negative 4.5 is out of the domain because this represents a radius. So that means that all we need to do is worry about positive square root of 4.5. That's our x value. Now, that's its radius. We want to find its height. Well, the height here is given by y equals 9 minus x squared. So, this is radius. To find the height, all I do is I plug it in. So I'm going to get y equals 9 minus square root of 4.5 squared. Well, that's just going to be 4.5. Cool. Solve the first part. Now we're going to take a look at the next two. So part B is asking us to find the cylinder with the largest lateral area. Now, lateral area is a term you may not have heard before. However, all it means is the side with the largest area. So if we're looking at our our cylinder, we're worrying just about this. Kind of the label on the can. That's it. And our formula for lateral area is just equal to 2 pi r times h. It's just the circumference times the height. Circumference is 2 pi r, and the height is just, well, h. Now, same as before, we want to write this as just one variable. Well, we know r here is x, and h here is going to be 9 minus x squared, because it's our y. So, simplify that a little bit, and we get 18 pi x minus 2 pi x to the third. And that's the formula for our lateral area. Same as before, even though we're dealing with something called lateral area, we just need to find the derivative. And our derivative here is just going to be 18 pi minus 6 pi x squared. And exact same as before, we're just going to set it equal to 0 and solve. Again, because x here has to be a positive number, we're going to wind up with, after a bit of algebra, x is equal to plus or minus square root of 3, but x has to be a positive number, so it's just the positive square root of 3. That's the radius of the cylinder with the largest lateral area. Well, to find the height, all we do is we just plug back in. So we know this is the radius, and the height would just be y equals 9 minus square root of 3 squared. Well, that's just 6. That would be our radius. That would be our height. So part C is asking us to find the maximum area, the dimensions of the cylinder with maximum area, meaning its surface area. And this is our surface area formula. This is 2 pi r squared. Pi r squared is the area of a circle, so the top and the bottom of our cylinder. 2 because we have 2 of them. And this is the lateral area formula we just looked at. Same as before, we just want this in one variable. Luckily, that's pretty easy. We've been doing this for quite some time. Oh, 9, not y. So, cool. That's going to be our area. And then if we simplify it, we're going to get this. And we know that even though this looks intimidating, this is going to be the exact same as taking the derivative in the previous two, because this is just a power series. So, all that's going to lead us to be is that. Well, we need to just set it equal to 0 and solve. This would be a bit more annoying for it. I'm going to spare you the details of it. But x is going to come out to be 1 plus or minus 2 radical 7 all over 3. You can just do the quadratic formula with it. Now we have plus or minus, and this is going to give us about either 2.0971 blah 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 blah, or negative 1.430. Same as before, x here represents a radius, so this one is out. This has to be our radius. So if we want to find the height, well, you just plug in, and I'll spare you the algebra because honestly, it's really, really similar. That's the radius, and the height is if you just plug into the original formula, this answer with positive, and you're going to wind up with 52 minus 4 radical 7 over 9. Now, the last part is asking us if the maximum volume cylinder has the same dimensions as either of the other area cylinders. Notice it doesn't. So it depends what we want to maximize. If we're talking about maximizing the volume, that's a much different cylinder than if we wanted to maximize the surface area, which is again a much different cylinder than if we wanted to maximize just the lateral area. So we talked about maximizing 3 different things here: the total volume, the lateral area, and the entire surface area. Our process for everything was the exact same. Make it into one variable equations, take the derivative, find the critical points, and evaluate. With that last one, the numbers did get a bit annoying. Okay, they were really annoying. They weren't just a bit annoying. They were pretty annoying. But we were still able to do the exact same thing. So you're going to take a look at the 2 homework problems. You're going to do them in your notebook, check them in the back of the book, and then, if they're right, take pictures of them and post them into Google Classroom. Stay well, folks, and I'll talk to you soon.